Okay, so welcome again, guys. Just a few administrative things to get out of the way before we start. So first, the project proposal. We announced it over the email list, but we wanted to make sure we announced it in class as well. It's due this Friday, the 11th. The proposal should be not that long, so 500 to 750 words, which is about a page. You should have in it your title, the Andrew email addresses of the participants so that we know who to assign credit for the project to. And then a description, which is the main things in the description are the data set that you're planning to use, which includes how you're going to get access to it, what's in the data set, and what do you hope to learn, right, from the data set, as well as what is the first step that you're going to take with access to the data set, and what are some possible milestones that you hope to achieve, and then what you think are success criteria, both minimal, you'll be very disappointed if you don't get those done, versus stretch, this was what you think, you know, if you do this, if you get all of the stretch together, you should be able to get an A+, right? This is what, you know, what do you think would be hitting it out of the park? Also, homework 2 is due 2 weeks from today. The PDF is up on the website now, and we'll send a link to the list pretty soon. And there's a midterm, which is Monday, the 28th, in class. All right? So any questions about any of the upcoming due dates?
So the proposal will be handed in the system?
Yeah, everything is electronically handed in. There's already a post up with a submit button, you know, submit proposal button. So just use that submit proposal button, and you should be able to paste in your proposal. We haven't got a format yet. We are willing to accept suggestions. The default is going to be that you're allowed to bring some small amount of notes in with you, but it's in general closed book and closed notes other than the small notes sheet. So does anybody think that's a bad way to run an exam, or you know, have suggestions for how many folio-sized pieces of paper you want to bring your notes in on? All right, cool. So I wanted to mention that while the hand-in server mostly functioned well, some students reported problems with uploading large image files. So that's even if they're below the file size limit of 950K per file. So we're going to try and track down and fix the cause of the problems. In general, if you have trouble with a hand-in server, let us know, and we want to fix it. But until then, I just wanted to warn people that that some students did experience issues, right? So if you're thinking of, basically, if it worked for you to hand things in that way in homework 1, it'll probably continue to work. But I wouldn't switch to a large image-based method of handing in your homeworks if you haven't already done that. All right? All right. And again, if people encounter issues, please send me bug reports. We don't want people to have trouble with the hand-ins, so let us know. All right. A little bit more on what to expect for the project. So people asked us a lot of questions in office hours about what appropriate projects are. The main thing that you need to ensure for your project is the availability of an interesting data set. Optimally, this is a data set that you currently have on your computer before you submit your project proposal, because data that's just about to arrive is notoriously bad at taking months or years to arrive, and that's not good for a semester-long course. So availability of an interesting data set, ideas for what interesting things are in that data set, right? So what do you hope to get out of it? And ideas for what is going to be your first algorithms to try for getting those things out of the data set. Okay? We're looking for interactivity, right? So it's a bad project proposal to just say, I'm going to run algorithms X, Y, and Z on data A, B, and C and call it a day. right? What we want is for you to say what your goal is for information to get out of the data set, and you apply these algorithms, and then you look at the result and adjust your course accordingly. Okay? So people also asked for suggestions about what might make good projects. So I put together, yeah, question.
Sorry, you mean if you were in the real situation of having this data and that was your job, you would change course based on the results? Or
Yes.
your algorithm should...
Right, right. You as a person should be willing to look at the results of the algorithm and change course, right? If your algorithm becomes artificially intelligent and also changes course, that's great, and you'll get an A+ on the project, but that's not required. More questions?
Actually,
Yeah.
You're talking about making sure you have the data set, but what about something that you're reliably getting more data on as it goes? For example, updates on the web that we know happen.
Oh yeah, that's fine, right. So if you wanted to do a, let's say a Twitter data set, and you had access to a Twitter feed that was getting bigger and bigger, that's just fine. Basically, as long as you reliably have, as long as you're willing to make the bet that you're going to have access to enough data by the end of the course, then it's fine. Had a question back there?
What about statistics that you're ongoing generating in other portions of your research?
Again, as long as you're reliably going to have the data by the time you need it, then it's good. This is just advice that data that you're depending on some other person to give you, don't. All right. So people asked for suggestions about what might make a good project, so I put together a few of those. The first one is machine learning on FAWN, which stands for a fast array of wimpy nodes. So the idea is, you know, it's easy to do machine learning on computers like this, right? That's sort of well-explored territory. But what if you had 200 high-end cell phones connected by the mother of all networks? Right? So an extremely different trade-off between computation and communication than what is typically used. How would you change machine learning algorithms to work on an architecture like this? Right? And so in particular, Alex has a box with, I think, close to 200 Cortex A9 cores, if you know what those are. They're basically what's in like the latest iPhone. The network is hundreds of gigabits of seconds and nanosecond latency, right? Which is, if you're used to ping times in the millisecond, right? That's a million times faster. So it's kind of a cool piece of hardware, and Alex is willing to open up access to try things on it. Questions about that one?
Where is that located?
Where is it located? I actually don't know. I assume it's in a server room in Gates, but it's on site. All right, another idea, wearable accelerometers. So Alex, again, is offering to buy hardware. Disclaimer, I don't know exactly what the hardware looks like, which is a wearable accelerometer. So you can buy wearable accelerometers, right, with a, you know, a Jawbone or a, you know, a Nike or Fitbit, right? But a lot of those don't give you access to the raw data. So you can get wearable accelerometers where you can get raw data from them, and you can use them to do things like figure out what kind of motion the user is doing, right? Or you could use it to make a person tracker, right? So you track how many steps somebody takes, and you use the accelerometer to locate them on a map, and you see how often you'd have to recalibrate against external reality in order to make that a viable solution, right? So I happen to know that I've seen somebody put an accelerometer on somebody's shoe, which turns out to be the most reliable place for getting steps, and use that to make something that's able to keep a reliable position for the person while they walk around a loop that's the size of you know, a good-sized building, which is pretty high performance for something that's just a, you know, an accelerometer located in your shoe. So, so that's another one. Video annotation. So you may have noticed that we've been putting up slides synchronized with video. That's done completely manually. But it would be a cool learning problem to try to take a PDF of the slides, extract the slides from it, take the video that's currently being recorded by that camera up there, extract the images from that, and do learning to try and make the most reliable matching of video to slides, right? So there's a lot of vision in this project as well. You're welcome to use, for example, OpenCV or any other third-party image processing library. The main thing to focus on for this problem would be the images, right? Would be the learning from the images, right? So this is, you could think of it as a multi-class classification problem. So you can get annotated lectures from us, right? We have, I think this is the 9th training example right now. And there's plenty on videolectures.net or techtalks.tv. And we guarantee you that we'll use your work if you open source it and make it readable code. Yeah?
So can this like synchronized by the time?
Right. So so you can use the ordering of the slides, which is obviously in the file. It does not, the training data would have the exact timing down to the minute, or down to the second, I think, of when the slide transition is supposed to be. But even down to the second, right, it could be off by a second or two from the actual slide transition. And in the test data, there wouldn't be those labels, because that's the point. You want to get those labels.
So I mean, so basically you want to match the video and the slide.
Yes, we want to match the video and the slides.
So in the video, you also have the slide information.
Right. So you can see, right, the camera is pointed at the screens right now. You can see video which is going through a bunch of analog degrading, right? So it's being, right, converted from the PDF on my laptop going out through the video cable to the projectors up there, projected on the screen going through the camera, right? So even that much degrading is enough to make it non-trivial to match the video with the slides. And we believe that a learning-based solution could be more accurate than one that wasn't based on learning. So did I see other questions about this one? All right. Educational data. So the idea here is MOOCs are getting really popular, and even in standard courses, you have a lot of online component, where the online component typically looks like a student sitting down in front of a computer and using it to drill with a certain class of problems, right? So you might have, for example, in middle school algebra, solve for x, right? And the student goes through and you give them a bunch of equations with an x in it, and you tell them to keep solving, right? And you watch what they do. And you can get sort of second-level feedback of the actions that the student is doing, right? So for example, if you make a form where they type each successive modification of the equation into a different box, you can get pretty detailed feedback about what it is that they're actually doing on the way to solving this problem. There is a freely available data set with millions of student interactions in it. It's the KDD Cup 2010. I happen to help run that challenge, so I know a little bit about what's in that data set and what might work for getting it out. But the goal would be, for example, you have hundreds of different problems. You might want to cluster them by what students do well or poorly on each individual problem. Or you have hundreds or maybe even thousands of students, and you want to cluster the students by what it is that they know. In other words, what problems they do well on. Right? And so this is a problem with a significant size data set. It's real messy. It was recorded inside actual middle schools, which is about as messy as you're going to get your data to be. And there's a lot of really interesting stuff in it. The KDD Cup Challenge in 2010 extracted a bunch of stuff from it, but there's still plenty of interesting stuff to go. So questions about that one? Yeah?
Can I ask a question about
the previous one? Video annotation.
So OCR will handle this problem?
OCR is a possible part of a solution to handle this problem. OCR is not perfectly reliable, even under the best of circumstances, and this is not the best.
Okay. So you think that in this situation,
still cannot recognize this.
I think it would be pretty easy using sort of standard vision-based techniques to get a 90 to 95% accurate solution, and that's not enough, right? If you want to actually use it for a course, it's got to be 99 point something % accurate, right? So the machine learning is in going from the 1 9 accurate solution to a 3 or 4 9s accurate solution. Okay, educational data. So with educational data, there's also the possibility of doing a qualitatively different thing, where you have a much smaller data set, but you learn a much more complicated concept. So what I'm imagining is you have a student who's using a graphics tablet like this one to solve a problem, and you capture all of their pen strokes. And they're doing something like, working out a 10701 problem set, which has a bunch of equations and derivations in it. Or maybe they're drawing diagrams for some problem in a different course. And you want to do learning on those, right? So there's a bunch of things that you can do ranging from very superficial recognition of the diagrams to pretty deep, right? You could try and learn a grammar of what's a good diagram for a particular problem. Okay? And so there's sort of a wide range of things you could do with data like that, and I'm happy to help you. I'm happy to provide the software and hardware to help you capture data like that. Let's see. So we've taught you a ton of different algorithms already, right? Perceptron, Watson-Nadaria, k-nearest neighbors, linear regression, logistic regression. And it might seem like a disorganized collection of here's one way, here's another way, here's another way, right? But I wanted to point out a few common threads that are in all of these algorithms, right? So there's a few different machine learning principles that we've been trying to show you examples of, things like maximum likelihood estimation or Bayesian inference. There's a few different optimization techniques that we've been trying to demonstrate, things like gradient descent or linear programming. And there's a few different things for designs of features to go as input to these methods, things like bag of words or kernel-based methods. Accelerometer. All right, so you should be able to, the goal for all of this, right, is after after going through all of these methods, what we hope is that you should be able to turn these three knobs to mix and match the different principles, techniques, and feature generation methods to take these machine learning methods and tailor them to your new machine learning problem. Okay? And so I'm going to go through and review what it is that we've said with a goal to sort of making that that sort of mixing and matching easier for you guys. So first of all, the machine learning principles. So let's just go through the ones that we've looked at so far, right? So we have maximum likelihood, right, which is which is apparently, there we go, maximum likelihood, which is something like, all right, what's going on here? There we go. OK. So maximum likelihood is, right, wow, I'm getting a ton of lag here. I don't know why. All right. There we go. Max over models M, the probability of the data that you've seen given M, right? Or equivalently, min over M, the log of the probability of data given M. Okay? Minus log. Thank you. Yes, don't min the log. That would probably be bad. Minimum likelihood is not a recommended principle. right? And so the text, the natural language way of saying that is that if my model fits the training set well, in the sense of assigning it high probability, then it'll probably be good on the test set too. And there are some circumstances where that's actually even true, right? And we've given you some examples where it is. Regularized MLE is the same thing, right? Except that you have min over m minus log. Oops, I can't write now. Minus the log of p of data given m, right? Plus some penalty of m, right? And simple models are, the idea is that simple models should get low values of the penalty term, right? And so regularized maximum likelihood is the same as maximum likelihood with the additional idea that simple models are likely to generalize better, right? So you have some penalty that enforces some notion of simplicity, and you'll take the simplest model that fits your data well, and then use that and hope that it generalizes better, right? Maximum a posteriori is the same thing, minus log p of data given model, right, minus log p of model, right? And the only difference, right, the same, this is almost the same, except that this penalty term here doesn't have to be a log probability, right? And then Bayes rule, right, you know Bayes rule, right, but it's that the probability of the model given the data. For some reason, I'm getting a huge amount of lag today. I wonder what the wonder if there's some way to fix that. Model given data is equal to the probability of the data given the model times the probability of the model over the probability of the data. Okay, looks like moving my laptop closer to the graphics tablet works. Technology. All right, so so any questions about these principles? You should be pretty familiar with all of them by now. Okay, so you know, you can never have enough principles. So here are a few more, right? We mentioned non-parametric, which is that the future data will look like past data, or maybe will look like nearby past data. So you just remember everything that you've seen, pull out a subset of them from your memory that are somehow related to the one you're trying to predict, and average their predictions, for example. And then empirical risk minimization. I don't know if we officially defined empirical risk minimization, but it is something that you've seen before, right? So it's going to be to minimize over models the sum over training examples I of the some loss function defined on your example I and your model, right? Plus a penalty term of the model. And so this is actually even more general, right? So before we had that penalized maximum likelihood, generalized maximum a posteriori by taking the log probability that was the penalty in map and turning it into just an arbitrary penalty function. Here, the same thing, we're taking the probability of the data and turning it into an arbitrary loss function, right? So in ERM, there doesn't have to be any probabilistic interpretation of the loss function, although of course you can use a probabilistic one if you want to. You can use a log probability. Okay? So we've given you examples of empirical risk minimization where there's no probabilistic interpretation of the loss function, right? So hinge loss is a good example of that. You know, they can work pretty well, right? And the nice thing about ERM is that it tends to be the principle that makes the fewest assumptions about the data. So for example, you don't even need IID data necessarily in order to make an empirical risk minimization approach work. Okay? But of course, the guarantees that you get for empirical risk minimization are the hardest to prove and or the weakest, depending on, depending on if you assume a lot, you get strong guarantees. If you assume less, you make your proof harder, right? So in general, right? So here's a list of some of the machine learning algorithms we've given you. One thing to check your own understanding is you should think and see if you can match each of these algorithms with the principle that was used to derive it. Right? So just to pick a few random examples, k nearest neighbor. Which one was that? Non-parametric. That's right. So that one was an easy one. How about linear regression if we don't make a Gaussian error assumption? Somebody said empirical risk minimization over there. That's right. So this is ERM. ERM, right? And if we do make the Gaussian errors assumption, right, it's maximum likelihood estimation, right? Maximum likelihood is a subset of ERM, right? So it is also correct to call this ERM, right? It's also correct. I think those are the only two that this one fits in. But basically, I'm asking for the most specific one that matches. Right. That was why I was hesitating. Right. Is you could call it map, but then it would be an improper prior, and so I don't know whether you want to count that as maximum a posteriori or not. But yeah, you could think of it that way as well. How about ridge regression? I heard. I couldn't hear any one of those. There were a lot of answers. Somebody want to? Yeah. Regular. That's right. So it could be regularized MLE. We can actually get more specific if we want to, right? Yeah, or we could call it map, right? Because the penalty term, you can actually interpret it as a Gaussian prior on the parameters if you want to. All right, trick question. How about Watson-Nadaria? Close, right? So it does use nonparametrics. It uses nonparametrics, but it also uses Bayes' rule to go from the class conditional density estimates to the class probabilities, right? So there's two different parts to Watson-Nadaria. First, you get class conditional density estimates, and that part's done with the nonparametric estimator, the Parson Windows. So I might as well put nonparametric here, right? But then to go from those class conditional density estimates to an actual label, you use Bayes' rule. Okay. Okay, cool. So it looks like everybody understands that pretty well. So, right, the nice thing about principles is that you get to choose which principles you follow. In general, the choice comes down to computational efficiency versus data efficiency versus the strength of the assumptions we're willing to make, right? So computational efficiency, right? Full Bayesian integration often does great for handling small data, but for big data, doing that integration in Bayes' rule can be a real bear, right? Unless you happen to have an analytic form for the integral. On the other hand, if you are in the sort of standard web-sized data world, then your only option might be to run stochastic gradient on top of a big parallel compute cluster, right? That might be the only way you can actually even look at all of your examples. Often, what we'll do is we'll wind up trying a bunch of different routes to get to an algorithm, right? So you can try, suppose I'm going to derive a maximum a posteriori estimator, and I'm going to make this set of assumptions, turn the crank, see what it comes out, and if it turns out that you can do it computationally, and if you have enough data, then fine. Otherwise, you go back to the drawing board, right? And so these sort of three knobs, they're interconnected, and we have to choose one based on its effect on the others. All right. So, another common thread is optimization, right? So a lot of these principles, you can see, they lead to a maximization or minimization problem. We can hope that the problem is convex. Sometimes it isn't. But we have to eventually select an algorithm to find, if not the optimum, at least a pretty good point, right? For Bayesian methods, it's actually even harder. Integration is sort of, it has optimization as a subproblem because you have to find the spots that have significant probability mass, and then you can add their contribution to the integral, right? So you have to do the optimization in order to find the spots that have, in order to find the good models. So for optimization, we covered a bunch of optimization techniques, right? So if we're lucky, we can just set the gradient to 0 and solve it analytically. That happens, but we're not usually that lucky. We talked about the gradient method. There's also the subgradient method, which is an analog of gradient for convex but not differentiable functions. It basically looks, the code is identical to the gradient method, so I'm not going to say anything more about it. Just, if you see that terminology, that's what it means. And we actually analyzed the gradient method, right? So if we have a, if it turns out that we have a strongly convex function, we can show that the log of the error, the negative log, is order of the number of iterations. Right, so that's what's called linear convergence, which is a pretty good convergence rate. But note that the condition number of the problem appears in the constant in the O notation, and that condition number can often be pretty bad. And so, so you're going to have to, the gradient method doesn't solve everything beautifully, right? If you have a very poorly conditioned problem, it can be very slow. We mentioned the stochastic subgradient method, right? So instead of doing all of the work to compute the gradient, you can just look at, for example, a random subset of your training examples to get an approximate gradient, and then from then on run the same code. It hurts the convergence rate, but it makes each iteration much cheaper. So that's a trade-off that you can make. We mentioned Newton's method, right? That has beautiful convergence under very strong assumptions. So if your very strong assumptions happen to be satisfied, do Newton's method. There's really no substitute. And if they aren't satisfied, then do something else. And then we also mentioned, we didn't talk about convergence analysis for linear programs, quadratic programs, other convex programs like semi-definite programs. And we finally also talked about other algorithms. Actually, these are other algorithms that we haven't talked about yet, but I wanted to at least briefly mention them. So expectation maximization, or EM, accelerated proximal gradient, the alternating direction method of multipliers. These are all algorithms that have different sets of trade-offs, right? And depending on what type of problem that you're trying to solve, any one of these might be the best method to use. So any questions about these methods so far? All right, so I wanted to give sort of a comparison chart of all of these things, right? So evaluating the convergence rate of all of these things, in other words, the number of iterations required, the cost of each iteration, and the strength of the assumptions that you need in order to apply it, right? So does anyone want to pick one of these boxes and fill it in with just looking for a qualitative number, like a number of stars from 1 to 5? I'll get you guys started. So for convergence rate, right? So I'm going to give Newton's sort of 5 stars for convergence rate. right, just to give you a scale, and stochastic subgradient is going to get 1 star for convergence rate. Because here, right, this is you double the number of bits in your solution with every iteration. Here you need the, you know, a number of iterations that's, you know, the square of 1 over the accuracy that you want, right, which is huge, horrible. Anybody want to fill in a few others? Right. Assumptions in Newton will give it 1 star because it requires a lot of assumptions. Actually, let's I don't know. Yeah, let's say low stars is bad requirement. So 1 star for Newton. That's a good one. How about the corresponding one for stochastic subgradient? Let's see. Let's go with 1, 3, or 5 stars. Raise 0, 1, or 2 hands to vote for that. Yeah. Okay, we have a bunch of people raising. Right. So stochastic subgradient has basically the weakest assumptions, right, which means the largest number of stars, right? Cost per iteration, right? Stochastic subgradient is cheap. Newton is your, you know, Michelin star restaurant. Right, we'll give it $5 signs because we're not going to talk about anything that's more expensive than that, right? And then I'm going to fill in the subgradient column myself because there's actually a technicality, right? So depending on what you assume, you can either, you know, assume, let's say, 3 to 5 stars worth of assumptions, right? And then you can get maybe you know, 1 to 3 stars worth of convergence rate, right? So in other words, if you assume that your function is strongly convex, that's maybe a 3-star assumption because it's pretty strong. But subgradient will then converge linearly, right? It'll take log of 1 over epsilon iterations. On the other hand, if you don't assume that, if you just assume convexity, you get a pretty horrible convergence rate, but it's a very, very weak assumption. Okay? And then the same thing, the cost per iteration of subgradient, I'm going to give it just a couple of dollar signs, right? It's more expensive than stochastic subgradient, but it's nothing compared to Newton's method usually, right? And because you guys haven't seen the accelerated proximal gradient, I'll just fill it in, and you can look it up if this happens to be the trade-off that you want. I'll give it 3 stars worth of convergence, you know, $3 signs worth of cost per iteration. Maybe let's actually just give it 2.5, right? Like it's just barely more expensive than subgradient. And the assumptions are weak, so we'll give it 4 stars. We'll 3 to 3.5, right? So anyway, the point is that it makes somewhat stronger assumptions than subgradient, right? But it gets a better convergence rate in many situations, and it's not that much more expensive than subgradient. Yeah?
So why is the stochastic gradient method better in terms of assumptions than gradient?
Well, it doesn't have to be, right? So gradient is 3 to 5 stars, right? So you can make very weak assumptions for the gradient method, right? And if you do, you get a bad convergence rate, the same convergence rate as stochastic subgradient.
Why is stochastic gradient is better in terms of assumptions if you just give it 5 stars?
Right. So you can, for subgradient, give it 5 stars as well if you want to, and then you get a 1-star convergence rate. If you make assumptions that are stronger, well, then I'll give you 3 stars for the assumptions you make, but you get a 3-star convergence rate, right? In other words, the point is the same algorithm has at least 3 or 4 different analyses. And depending on which analysis you go, you can either have 5-star assumptions and 1-star convergence rate, or 3-star assumptions and 3-star convergence rate, or anything in between.
So why is stochastic convergence has 5 stars?
Because there is no other analysis for stochastic subgradient, right? The only analysis for stochastic subgradient is that it is very weak assumptions and very bad convergence rate.
My understanding, if you want to make stochastic gradient run well, you have to have redundant data sets.
Right. So I'm talking only about the performance of these algorithms in terms of converging to the optimum of the thing you're trying to optimize, right? If you want to have something generalize well, it is true that you have to assume something about your data set, right? But right now I'm not talking about generalization because you can use these methods to optimize any of dozens of objectives, right? And the generalization is going to depend on which one you optimize. All right? Any other questions about the comparison chart?
What about combinations?
Combinations of these, yeah. So that's actually a good idea, right? So if you have, for example, something that is strongly convex in a region around the optimum, but not globally, right? You could use something cheap like stochastic subgradient to get you to the region around the optimum, and then run Newton's method to get you to polish the solution and get you all the way, right? And in general, tons of combinations of these are possible. And I've only put the 4 major, categories of methods up here, right? There's probably as many optimization algorithms as there are machine learning and optimization researchers. And so combinations of these or variations on them are often a good idea. Other questions? All right. So next, common thread is features, right? So the situation that you're usually in is that your customer or your collaborator or your boss hands you, and a SQL Server database, right? Something in like the least convenient possible format. And you need to turn it into valid input for one of these algorithms, right? And what that means is that, you run a whole bunch of joins that take forever, and you use them to extract your favorite set of features. And then you look at the data and you try and figure out some way to throw out outliers where somebody, accidentally typed -infinity into one of the boxes of your database form, right? And right, so you go through this whole big process of taking the data in the form that it came to you and turning it into valid input for one of these algorithms, right? And basically, the only way to teach that process is by example. And so we've given you a bunch of examples, right? You've had a hands-on example with the challenge problem in homework 1 and homework 2. And then we've given you examples like, for example, if you have text data, you might want to think about turning it into a bag of words set of features. Or if you have real numbers, you might want to consider turning it into low-order polynomials or taking the log, right? If you have things of very widely varying magnitudes, right? Images, you could look at the optical flow, the SIFT features, right? There's a ton of them. And basically, with each different data type, you get practice in figuring out how to convert it. The typical option is that your feature vector in the end is a finite length, a fixed length vector of real numbers. Maybe 100 of them, maybe 1,000,000 of them, but it'll be fixed length. We also mentioned kernels, which are cool because they let you deal with infinite length vectors of features without having a loop for i = 1 to infinity in your code, which I don't recommend, by the way. It'll run out of the time limit on this AutoLab. So right, so you can have infinite feature spaces, and you can deal with things that are very difficult to featureize, right? So you don't need to figure out how to featureize a graph or a tree or a string. You just use a kernel that's designed to accept those as inputs. All right? So where does it all lead, right? So all of these different knobs that you can turn, right? They lead to different algorithms for the same qualitative problem, right? In other words, we could give you a natural language problem statement on a homework, and you could come up with a dozen different ways to solve it, right? And that's, in fact, what we did. Different principles will lead sometimes to different algorithms, or sometimes they'll lead to the same algorithm, right? So ridge regression, you can, as we said earlier, you can have it as conditional maximum a posteriori under a Gaussian assumption, or you can have it as empirical risk minimization under the squared loss, right? Or they can sometimes just give you similar answers, right? So for example, linear discriminants, linear classifiers come up with a wide variety of different assumptions that you could make. And so we gave you a few different examples of that. Excuse me. And I think it's kind of cool to notice that you know, this same idea, a linear classifier, comes up repeatedly, right, with a wide variety of different assumptions that you could make, which sort of, in my opinion, makes it likely that linear classifiers are a good thing to know about, right? If all roads lead to Rome, then Rome must be a good place to go. Right? So, so that's the end of the sort of taking stock, the review of what we've done so far. Does anybody have questions so far? Yeah.
We haven't really said anything at all about like confidence in our predictions.
We will get to confidence. It is a can of worms, but we will get to it.
And so, is it just that it's a can of worms, like that's why we haven't talked about it, or is there sort of an underlying reason why we don't care as much about it?
No, no, we do care very much about confidence. And the reason we haven't talked about it yet is that we don't want to open that can of worms just yet. Yeah, we can invite the robins and open up that can of worms pretty soon. Any other questions? All right, so now Alex talked about Lagrange multipliers at the end of class last time. He did it very quickly, so I wanted to go through them again. This happy-looking fellow is Joseph Lagrange. And his multipliers are a really useful technique, so we're going to spend a little bit of time on them. But in particular, the end goal of this sort of subsection of the course is that Lagrange multipliers lead to a very famous machine learning method called the support vector machine. And what we want to do is give you enough tools over the next lecture or two to get you to the point where we can introduce the support vector machine and tell you something about its properties. So let's dive in. So if you remember Newton's method, right? So if you wanted to minimize a function f of x, right, with no constraint on the function, what you did was you made a Taylor approximation of it, right? So we have a function from d-dimensional real space to a single real number, and we approximate that f of x plus delta x is approximately equal to f of x plus f prime of x dotted with delta x plus delta x transpose h delta x over 2, right? And then I'm going to ignore all terms higher than second order, right? And then if we take the derivative of this with respect to delta x, right, we get f prime, sorry, not transpose, but prime of x plus, this should be here, h of x, right? H of x delta x is equal to 0, right? So we take the derivative with respect to delta x, set the derivative to 0, and that's how we find the delta x that's predicted to get us to a local optimum, right? And so in particular, what we do is we treat this guy, f of x, and that guy, we pretend that they are constant and just solve for delta x, right? And so when we do that, what we get is something that looks like h delta x plus g equals 0, right? So any questions about Newton's method? OK, so the intuition for Newton's method is that the predicted change in the gradient is h delta x, right? When you make a change of delta x, you predict that the gradient is going to change by h times delta x. And so we're using h delta x to cancel out the current gradient and get us to a point where the gradient is 0. In other words, we're at a local optimum. OK? So now suppose that we have equality constraints, right? So we want to minimize f of x such that p of x is 0. And so f of x here is the contours, and p of x is this green line, right? And if you look at this, oh, darker, by the way, is lower, is better, right, on the contours. So you should be able, with a little bit of thought, to look at this and tell me where the local optima are, right? Anybody want to hazard a guess where the local optima are of f of x subject to p equals 0? Left side, like right here? Yep. Yep, that's one. There's another one. On the right side, yes, right? And there's actually even a third, which is probably a local maximum right here, right? But in general, the way you do this graphically is you look for places where the contours of f are tangent to the constraint surface, right? Because what that means is that if you want to move up or down, you have to move perpendicular to the constraint surface, and that's not allowed. And so that's a local optimum, a local minimum, maximum, or saddle point, right? So what that means mathematically is we look at, right, so here is the gradient of f, right? And here, right, the gradient of f is pointing this way, and here the gradient of f is pointing that way, right? And so what we want is that the gradient of f prime of x, is orthogonal to the constraint, right? So the gradient and the constraint is p of x equals 0, right? And so the normal to the constraint is the derivative, the gradient of p, right? And saying that they're parallel is that f of x is equal to some multiple of p, f prime of x is equal to some multiple of p prime of x, right? So that went by quickly, so I'll repeat it, right? So for p, we have its gradient, right? So this is p prime of x, right, for that x. For f, we have its gradient, which is going to be like this, right? This is f prime of x, right? And what we would like is to find a spot where, so let's say it's this one, right? So actually, let's say it's this one, right? So f prime is this one, right? And p prime is going to be, actually, just for clarity, let's make p prime really long. P prime. We'll put it where it's easier to see, right? And so f prime and p prime are pointing in the same direction, which means that there's a real number lambda, so that f prime of x is equal to lambda p prime of x, right? So do people have that? Because that's going to be pretty important. Yeah?
So just to clarify your notation in this case, your primes don't refer to derivatives.
No, the primes do refer to derivatives.
Okay.
The prime means the gradient in this case, right? The d-dimensional vector, which is the direction of largest increase, steepest increase, right? And so here, for example, the direction of steepest increase of f is right that way, right? And p, the convention I've taken is that it's increasing to the right of the curve and decreasing to the left of the curve. And so the gradient is pointing to the right. And we don't actually know the magnitude of the gradient. And so I've just guessed that these are the magnitudes of the gradients there, right? Yeah?
So the p prime there is like with the sign. So why does the sign go to the?
Let's see. So why are the signs the way they are is the question. So I've just taken the convention that the sign of p is such that its gradient is pointing to the right of the curve, right? So this is its gradient here, that's its gradient here. F, you can see which direction it's pointing, right? Here it's low, here it's higher, and so the gradient has to be pointing perpendicular to the contour line in the direction of increase, right? And so here are where I've sketched which direction the gradients of f are pointing. And so it happens that the f prime is pointing to the left here, and p prime is pointing to the right, right? But they're still parallel, right? Lambda can be positive or negative, and they're still parallel. Okay? Yeah?
So if this graph multiple maximums as well, are we just calculating all of this manually? Or
Right. So with Newton's method or any gradient-based method, you have to check whether you hit a local minimum, a local maximum, or a saddle point. And there's a bunch of ways to do it. The simplest way is to record function values and see if they're getting higher as you do your iteration or lower, right? But there are conditions based on the derivatives as well that you can use to check. For this course, we aren't going to worry about it. We're just going to assume that you always hit a local minimum, which is going to be true if you're optimizing a convex function because there are no local maxima. Yeah?
So P here you're defining as the green hypersurface, right?
Yeah, P is the green line here.
Shouldn't the gradient of P should be on that hypersurface?
No, so it's an implicitly, so the question is, shouldn't the gradient be pointing along the green line instead of perpendicular to it? And the answer is no, because if we said that a set, so let's say if we had some function, call it, let's say, q of t, where t is a real number and q is a d-dimensional vector, right, for t in the interval 0, 1, right? So that would be, this is a parametric definition of a curve, right? It's the output of some function. Here, this is an implicit definition of a curve. It's some function is equal to 0. In this representation, the gradient of q points along the curve. In this representation, the gradient of q points perpendicular to the curve, right? So for example, right, if we said, you know, x squared plus y squared equals 1, right? That's a circle, right? And if you look at what is the gradient of x squared plus y squared minus 1 on this circle, it's going to be pointing like that, right? The gradient will be 2x, 2y. Okay? So that's a good question because there's more than one possible way to represent a constraint surface. The way to do it for optimization is almost always implicitly. Okay, so I think now is probably a good time to stop and take a look at the homework. Is that good? Okay, so Carlton has a presentation about the challenge problem that you guys saw for your homework. Let me just bring it up. Sorry, I forgot to.
Not quite right.
Uh-oh, I'll fix that.
Thanks.
So the fix for that, by the way, is this little thing with the fit screen thing. So, and you use the arrow buttons to move around.
Thanks. All right. Can everyone hear me? We good? All right. So I was just going to talk to you a little bit today about the challenge question from Homework 1. So this was a new initiative this year where we sort of wanted to get you guys to work with some sort of real-world data and get a feel for not just these toy examples and algorithms in class, but like the feeling for really solving a problem and sort of all of the trials and tribulations which come along with that process. So, welcome to the Homework 1 challenge question. I hope you all enjoyed it. Perhaps as much as I enjoyed writing it, but we'll see.
Or debugging the server.
Or debugging the server. That was not as much fun as it could have been. All right. So a little bit, just a quick recap in case anyone's forgotten since the hand-in date. I gave you a bunch of labeled data, and I asked you to write a distance metric, which did a good job of classifying our hidden test set. And we scored your solution based on how well your metric did. So how many examples in our hidden test set your metric got right. And we didn't really care what you wrote in terms of your distance metric, as long as it gave a good performance. It didn't have to match something we gave you in class. You know, the sky was the limit, really. All right, and what was the difficulty? Well, the data wasn't exactly nice. But this is kind of what you come to expect when you deal with real-world data. So what was it? So the data you were dealing with was actual data from a UCR insect classification contest. And this was a really big online coding, machine learning contest run by the University of California, Riverside, where they gave out this data set, and they actually asked people to write this distance metric. So like researchers from a whole bunch of different research groups across the country actually participated in this contest. And they asked you, so what that was they asked you to classify insects based on the sounds they made. So the data you had was sound bites from a bunch of different insects. And what you were trying to do was you were trying to say, well, I've listened to this insect, what sort of insect is it? All right. And so as I said, entire research groups from many universities, they worked together for months to solve this problem. We gave you guys 2 weeks. We didn't tell you what sort of data you were dealing with. Like, I said, here's some data, just go, have some fun. So they had a few advantages on you. So here's the real question. How did you match up? How did the 701 students do versus the researchers? So here's you guys. This may not be the final table. This is the table when I made this presentation, like last week. So I apologize for any inaccuracies if anyone's moved since then. And here's the researchers. So, I think you guys did pretty well. That's kind of impressive. The first thing I'd say is you had better names, like way better names than anyone of the research teams. But the performance, that's pretty good. I mean, there's only one research group that beat you. There is the small caveat. Their data set was slightly larger and slightly harder, but not by much. When I went along and ran some of these, I actually went and like compared some of these algorithms on the test set, which I cut out for you guys. And the performance was a few points better, but not by much. So that's a really pretty good job.
So, so we also concerned the classifier. We only five minutes need to do.
Okay, so the contest was strictly limited to using a distance metric. What you did was exactly the contest. The contest was to write a distance metric which classified these insects. So
they also use like 5 minutes maybe to do.
Exactly.
Okay.
Yep. All right. So I'm going to talk to you now for anyone who didn't, or anyone who's interested, is how I would have gone about solving this problem. So the trick here is that, well, what I'm really trying to get across here is that, like, this sort of problem, you can't just throw algorithms at it. Like, we teach you these algorithms like k-nearest neighbor in class, right? But if I'd just taken like k-nearest neighbor and just throw in Euclidean distance at this, as probably most of you did as your first attempt, it was terrible, right? Like, you looked at you threw like Euclidean distance k-nearest neighbor at it. You looked at the leaderboard and you're like, well, damn. So here's how I would have gone about constructing the solution. And this is the sort of process I want you guys to go through, where it's not about knowing more fancy algorithms. It's about using them well. It's about looking at your data and making smart decisions about how to apply them and which algorithms to apply. All right, so this is how I went about it. And this is how you can go from 0 to hero in 5 easy steps. This is not the only solution, and it's probably, in fact, it's certainly not the best solution. Someone's written a better solution out there. But I like to think it's not a bad solution either. Maybe just for my own personal satisfaction, but moving on. All right, so step 0, the raw data. Here is some raw data. I chose 4 insects from 4 different classes and plotted them. Please plot your data. It helps you understand what sort of data you're dealing with and lets you make smart decisions about how to deal with it, what algorithms to apply and how to apply them. Now, this data kind of sucks. It's kind of hard to tell them apart. Like, you're staring at this. There's 4 different classes here, but they're not very obvious. So let's go about trying to make them more obvious. All right. So here I've just selected one of these examples and blown it up. No transformations yet. So here, pre-processing. What I did from here is I cut out the excessive dead zone, the space at the end of each signal. Silence is not very informative. Like, clearly what I really care about, and the distinguishing feature of each data set, is the spike in the middle. So let's just make that more obvious and sort of center the data. So what I did was I went along and I took each data point and I cut out that noisy bit in the middle. Fancy machine learning? Not really, but effective. All right, step 2. I did a Fourier transformation. Now, this is a natural thing to do in this domain because Fourier transforms work in terms of signals. So clearly when we plot this, it was some sort of repeating signal. And what I cared about in this sort of case is not where the spikes were located, but where they were located relative to each other. Okay? So this was the only slightly tricky part in the whole process. But generally speaking, whenever you see a signal, like something that looks like a sound file, you should apply a Fourier transform. All right. But the problem is our Fourier transform is still a bit messy. Like you can see these spikes all over the place. So now I smooth the data out. Again, nothing fancy. I just applied like a moving average across the whole thing. And this is a much easier data to work with than the spiky thing here. Yep. The next thing I did was peak detection. So I went and said, well, what I really care about is the location of these spikes. I don't really care about like what they look like. I just really care where they are. So when I found the peaks, again, very simple, nothing fancy. And I calculated the distance between these peaks. Now, each of these steps could be theoretically motivated by knowing the data you were dealing with and like working in the domain. But really what I did was at each step, I looked at the data and I said, what's the distinguishing feature? How would I go about processing this?
Question.
Mm-hmm.
Are you dealing with the absolute values of the Fourier transform or just the real parts?
I cut this down to the real part of the presentation. You can use the imaginary part as well if you'd like. I didn't see any benefit in plotting it here. All right. And so what I actually did here for my distance metric was I calculated the distance, the average distance between peaks in my data sample, and that was my one-dimensional representation for each sound file. So what I did was I took a sound file consisting of like 16,000 numbers, like a signal that does this for like a second, and I reduced that down to a single number, which is the distance between peaks in the Fourier transform. And then I said the distance between 2 points is just the difference between these two real numbers. Okay? And so how did this do? Well, that gave 77% classification accuracy. So, not a terrible solution. And again, like I've reduced each signal here to a single real number. That's kind of good because comparing like 16,000 dimensional vectors is kind of slow, right? I mean, you saw when you submitted a solution, it just chugged and chugged and chugged for quite a while. But comparing the distance between two real numbers is really fast. Thank you. And we can also, the other thing we can do is we can store these in really small amounts of space. So storing sound files, you know, most of the space in your computer is taken up with movie files and sound files. Storing one-dimensional real numbers, very small. So just here at the end, some examples. So these are the 4 classes reduced to their one-dimensional representations. So you can see that each of them has different peaks. The peak space in each example clearly distinguishes which class of insect I'm from. All right, so the take-home messages. Real-world data is not nice. Visualize your data. It will help you. Look for patterns in your data and try and exaggerate them, make them more clear. And decide which algorithms are appropriate based on these analyses. Don't just apply algorithms blindly. There is no point in throwing random algorithms at your data and hoping something will work. It will not. And finally, look forward to homework 2, challenge question. When I wrote this, it was almost here, but I think at this point it is here, right?
Yeah, I think it's up.
Fantastic. Yes? I'm sorry?
He wants the code for your solution.
The code for my solution? It's not in a very nice format right now. If I get the time, I'll bring it forward. No promises. Email me. I'll try.
This seems like a good spot to leave, so we'll get back to Lagrange multipliers next class.
Thank you.